Hello?
Hey guys, can I get a sound check?
Yeah, we can hear you,
Hello?
Professor.
Yeah, same.
Hey guys?
Hello?
Can you
No,
hear
we
us?
Hear you. We can hear you.
Hey guys?
Yeah, we can hear you. Can you hear us?
I can just hear you. I have to change the setting.
Okay, good.
Thank you guys. All right. Okay guys, so let's start. Any questions first of all, up to now? No? Okay. So let me just, gonna keep telling you guys these transfer characteristics of the diode till you're sick of hearing it. So again, we have this diode device, and if I hook it up like this, whoops, wrong. So this is the diode, this is the input voltage, and this is the current. And if I draw the current versus voltage characteristics of this thing, I'll end up with something that looks like this. And the equation for this current versus voltage is I sub D is I sub S exponential of VD over VT. Oops, I keep doing this wrong. Sorry, guys. Change that to a parentheses minus 1. Okay, so this is the total equation for this thing. And VT is 25.9 millivolts or 26 millivolts at room temperature. And I sub S is, a function of the diode design. I think pretty much in every case in chapter 3, you'll be given an I sub S. And then if I can do some approximations here in the different regions. If we're talking about anything less than 0, so if VD is less than 0, then this term goes to 0, like a large negative exponential goes to 0, and you end up with I sub D is minus I sub S here. And this I sub S, again, is a very, very small number. So depends on the design of the diode, but you're talking about, these are 10 to the minus 16, 10 to the minus 17 amps. So very small numbers. And then if you look at on this positive side of the curve, when V sub D over V sub T ends up being, I don't know, much greater than 1, this exponential term just blows up, gets huge. So it gets much larger than this minus 1 term. And then you can just call it over here, you'd call ID is equal to I sub S exponential of VD over VT. I'll say approximate. Okay, so this is the exponential model of the diode. Okay, so this is how a diode works, but where we can, because it's difficult to deal with exponential functions, etc., like this, like that, what we try to do is we create a very simple model called the ideal model of the diode. And this thing really looks brain dead, very simple. So you just have this. If you plot VD versus I sub D, it's the same device. Okay, guys, it's the same diode, same circuit, but I've just got a really simple approximation, okay, of how this is worked just to make my calculations easy. And so in this case, when VD is bigger than 0 volts, greater or equal to 0 volts, then the diode looks like a closed switch. Okay, and when VD is, so that's anything out here, looks like a closed switch. Remember, this slope of ID versus VD is the slope of 1 over R. So when the slope is infinite, the slope is infinite, means R is 0. R is very small. Okay, and out here, where VD is less than 0, the diode looks like a open circuit, open switch. So this is R of diode is equal to 0, and this is R sub diode is equal to infinity. Again, this is the same device. We're just doing, if I was going to draw the exponential 1 on top of it, it's like approximating this thing. Okay, so that's called the ideal model. Now, notice that it does, this is maybe for a bunch of circuits, it might be oversimplifying things because this is assuming right at 0, the diode turns on. Whereas we've seen it's effectively at some, it's got this exponential, so it's more like it's got an offset. So it looks more like something like this. This might be a better model where I have the same thing, except the diode turns on at some VD on. And at some VD on, that's typically, 600 to 800 millivolts. I mean, it could be less, it could be more, but that's a pretty approximate range. If it ends up being at any point in your calculations, if it's like 1.2 volts or, I don't know, 300 millivolts or something, you're probably in the wrong track. So this particular diode model is called the constant voltage model. And in this model, when VD is greater than or equal to VD on, then the diode looks like a closed switch with a battery of value VD on across it. Okay, and then VD is less than VD on. So anywhere out here, the diode looks like an open circuit again. We've got the battery still, just for the sake of completeness, but in the second case, your circuit's not going to see that battery. So in this case, what happens is you basically, at VD on, you turn on, but this battery allows you to sort of make it look like you've got this voltage delta, this offset where the thing turns on. Okay, and so this is just another model of the diode. So we've got 3 models of the diode with different degrees of complexity. Okay, so this is the most complex model. Sometimes you have to use this. We'll see an example maybe later in this lecture. This is the least complex model. But I mean, by that, I mean that, well, this is the least complex. It's got, the simplest model, but also it's the easiest one to analyze when you have a bunch of circuits, circuit elements, etc. And this is somewhere in between. This is pretty easy, but sort of I don't know if I'd even call it medium, but yeah, so somewhere in the middle complexity. But probably a better model. So just to give you guys an idea, like at work, I hardly would ever use this, very, very rarely, when I'm like designing a very, very sensitive analog circuit. I would also very rarely use this because it was a little too simple. So I would almost 100% of the time, I would use this constant voltage model to sort of estimate what's going on in the circuit. And then I would use SPICE simulations. Okay, so let's do, I think this slide says the same thing. So again, these are all exactly the same device. Okay, don't get confused about that, but they are 3 different models that are just, this would be the easiest to use in a circuit. This is the most difficult. And, this is probably like a more reasonable approximation. And when you get to the homeworks or, the quizzes, final, whatever tests, basically you'll get told for the most part, you'll get told which one of these to use. Okay, so you don't have to guess for the time being. Okay, so now let's do a couple of more examples of these circuits. So let's see, what do we got? So is this the first one? Well, let's do this one. Okay. So, whoops. We've got any questions about the different models, by the way? No? Okay.
Professor, are we in chapter 3?
Yes, we are.
All right, thank you.
Let me see. I don't know, we're probably in 3.2, I think. We're around 3.2. Something thereabouts.
Thank you.
Sure. R2, and then this is a diode. Okay, so we're going to do we're going to try to plot the V in versus V out curve. Okay, the transfer function. And we're going to do it for the ideal model. And we're going to do it for the constant voltage model. Okay, so let's do it first for the ideal model. So I'm going to do what we did, a bunch of times last time around. First, assume Vn is very negative. Okay, so if Vn is very low, this point is very low compared to ground, means that the diode is off. Okay, so basically I end up with this circuit. Okay, notice there's no current flowing anywhere out of Vn because this is open. So if there's no current flowing, there's no voltage across R1, meaning that V out by KVL, V out is Vn plus whatever voltage is across, or minus whatever voltage is across R1. But because there's no voltage across R1, V out is just equal to Vn. Okay, so that's very negative on a very negative input out here somewhere. And then when Vn is very positive, meaning this guy is very high, this point is higher than ground, significantly. So it means the diode is on. So by the way, this is, in this case, I'm doing the ideal model first. And for an ideal model, an on diode, sorry, this one had the off diode. Off diode looks like just an open switch. Okay, so in this, the case where Vn is very large, we have an on diode. And in the ideal case, we have it just looks like just a closed switch. So we get R1, R2, closed switch. Okay, and then, so in this case now, we do have a current flowing from Vn to ground. So there is a voltage drop here. In fact, we have kind of a resistive, not kind of, we have a resistive divider case here. So V out is equal to R2 over R1 plus R2 Vn. Okay, so we got two slopes. When we're very negative, V out is Vn. And when we're very positive, we have R2 over R1 plus R2. And then we got to figure out where this thing crosses over from one to the other. So we got to figure out where the crossover is. And to do that, the crossover by definition, both this and this have to be true. So V out is equal to Vn is equal to R2 over R1 plus R2 Vn. So the only place where this can be true is when Vn is equal to 0. Right? Otherwise, I think for any R2 and any R1, this would not be the true. I think it's only when Vn is equal to 0, it's true. So V out is equal to Vn is equal to 0 is the crossover point. So if I was going to draw this, Vn versus V out, the crossover point would be here. Anything negative, V out would be equal to Vn. So we'd have a curve with a slope of 1 on this side. Anything higher than this point, V out would be R2 over R1 plus R2 Vn. So it would have another slope. And that slope would be R2 over R1 plus R2. So this is like very much like the problems we were solving last Thursday. Any questions about this?
Sorry, I need anything more time.
Sorry?
Can you scroll down a little bit?
Sure. Do you want me to just let you take the notes, or do you want me to talk slower?
No, I just need to look at the notes more.
Professor?
Yeah.
So I'm just trying to check right now. On the left side, the reason why V in and V out are the same is because there's no ground, right?
Yeah. There's no, the one way to look at it is for V out not to equal to V1 by KVL, you'd have to have some voltage across R1. But because there's no place for current to go, because this is open, there's no place for current to go. So there's zero current. So there's zero voltage across R1 is how I look at it. Does that make sense, Nelson?
Yeah, that makes sense.
Okay. Arthur, are you good?
Yeah, I'm good.
Okay. Am I talking too fast, guys? I went for a run right before class. So I might be a little too much. Might be a little too much up.
I think you're going a good speed.
Okay. Okay. But slow me down whenever, or stop me whenever you guys are. Whenever I start babbling too much. Okay. So that was the ideal model. So now we're going to solve exactly the same circuit for the constant voltage model. Okay, so we're going to do this one. So let me just redraw the circuit so we have it in front of ourselves. And again, we want to plot V in versus V out. Okay, so this is for constant voltage model. Okay, so same analysis. So when Vn is very negative, the diode diode D1 is off. Again, this is like minus infinity, so it doesn't matter if D on gets off at VD on or at 0. You know, we're talking about a very large number here. So when this goes very low, this thing just turns off. Okay. Now in this case, I'm gonna draw it, but it doesn't really matter. In this case, because we're talking about a constant voltage model, the diode looks like an open switch. But whoops. Looks like an open switch, but there is a VD on volt battery in series with it. This, you know, when it's off, it really doesn't matter because as you'll see, R2, our switch is open and we put the battery here. V out, V in. Notice it's exactly this guy. Looks exactly like this guy, but there's no battery here. In this case, because we've got the constant voltage model, there's a battery. But when the diode's open, when this thing is open, or sorry, when the diode's off and the switch is open, it doesn't matter. Like you don't really see the battery, the output, V out doesn't see the battery. So there's no current flowing, so still V out is equal to V in. Okay, now where it gets more complicated is when Vn is a large positive number. There D1 is on, which means that the diode looks like a switch with a battery. So okay, now we do have a different circuit, right? So here we have this guy, which looks like a voltage divider with a VD on offset. Here, it's just a voltage divider. Okay. Now you could probably guess what does V out versus V in gonna look like with this battery. but I suggest you work it out the long way, because there will be some problems in the homework, and I don't know, they might show up in a quiz where it won't be so obvious what's going to happen. So I'm just going to pretend I don't know what's going to happen. I'm just going to work out the equation like step by step. And so, or at least the way I do it. So you guys can see what's going on. Again, if you don't take, like if you take a shortcut, you might get bit. Okay, so my advice is don't take a shortcut and actually calculate. Okay, so that, like I mentioned, we want to figure out by KVL, really we want to figure out what voltage drop we get across this guy. Okay, so basically that we got to figure out what current is flowing here. And so this current, this I, okay, goes across this R1, across R2, and ends up in VD on. Okay, so this current looks like V out minus V in, sorry, minus, oops. So this current is the same one that flows here. So this is current goes through here, goes to, let me just draw it better. Okay, so if we just look at the current in terms of Vn, so let me actually do this. So if I start at Vn, start here, and this is my end point. Well, let me actually do the full KVL for you guys. So Vn minus I R1 minus I R2 minus VD on is equal to 0. So basically that looks like this voltage minus the voltage across this, minus the voltage across that, minus the voltage across that, so it closes the loop. Okay, so if I rewrite this for in terms of I get Vn minus VD on over R1 plus R2. Okay, so this is just KVL. So this is also just rewriting of KVL. Any questions about that? Okay, and then basically V out is the same current I flowing across R1. So it's Vn big. So let me write the KVL from V out to Vn. So Vn minus I times R1 minus V out is equal to 0. Okay. Basically this guy minus that guy also just closes the loop. Okay, so V out is equal to Vn minus I R1. Any questions about this stuff, guys? You got to be really comfy with this stuff. I mean, we'll see like in the homeworks and in the quizzes, etc. You'll see this over and over again, this kind of analysis in this chapter.
Professor?
Yeah.
So, like, I guess I have a question. So, like, the loops, how exactly does this loop exactly? Because isn't it only one way? Like,
well, let me draw it fully. Maybe because I'm taking a, I'm sort of drawing it like I would. So the way the loop looks like is this. So let me draw the. Move these guys over. So everything goes back to ground. Okay, and ground is the same node. Okay, so this is like, let me just redraw it here. Like this, oops. So everything is with respect to this common voltage, which we'll call ground. So then I talk about V out, VN. VN is the voltage from here to here. It's the voltage across these two nodes. Okay. IR1 is the voltage across these two nodes. And V out is the voltage across these two nodes. Okay, and notice this is the same node as the bottom voltage for Vn. Does that make sense, Nelson? Was that your question?
I mean, I guess that answers it. Like, yeah, because I was just wondering, since it's like, you know, KVL is supposed to be a loop. So
Yeah.
I'm assuming that this is just not shown, but these two, the V in is actually connected here with like a,
I mean, there'd be like a,
Source.
you could say it's a voltage source here, I guess. If you wanted to say an input. But basically you've created a voltage between this node, whoops, sorry. When you see this, because voltage is across something, right? It's two points. So you could say Vn is the voltage difference between this point and this point. Or you could draw like an actual voltage source here, if you want. Okay, but then you have this sensing node. This place, you're sensing that voltage. So it's also the voltage drop between this point and this point. It's this delta voltage.
so is there something else on V out, or is it just like,
It's just floating. So it'll be your multimeter or something. Okay, so
okay, I see.
so yeah, if I was gonna draw this, like how it really look like in real life, you would put a battery or voltage source here. And I don't know what the symbol for a multimeter is. Across this. And what a multimeter does is it can read the voltage on V out without drawing any current. Okay, the multimeter is not interfering with this V out by drawing any current. You're just putting it across and reading a voltage from here to here. So that's what it would really look like in real life.
Yeah, that makes sense.
Okay, yeah. Okay, so any other questions, guys? Again, I can't emphasize this enough to like get really comfortable with like analyzing these kind of circuits for chapter 3. Okay, so back to it. Now, what we were doing was, again, V out is Vn minus IR1. Okay, so we plug in Vn. We plug in the equation we had for I. Here we get Vn minus Vd on over R1 plus R2 times R1. Yeah, sorry guys. Okay, and the rest of it is I'm just moving stuff around. Let me just write it for you guys, but is so Vn 1 minus R2 is times R1. Okay, so this guy will be Vn R1 plus R2 minus R1 plus R2. Okay, so these guys cancel each other out. Mhm. And then basically we get V out is equal to Vn times R2 over R1 plus R2 plus VD on R1 over R1 plus R2. Okay, so this guy looks like an offset. So if I was gonna look at the slope of what we would look like at V out versus Vn, so just the slope, basically be this ratio, right? Because this guy is an offset on that line. So a line looks like if I was gonna draw y is equal to, you know, ax plus b. Y is V out, X is Vn, A is the slope, and B is this offset, okay? But the slope looks like the same slope as we got here, but it has an offset built in. So that kind of immediately tells you you're probably not going through zero. So you're probably not doing this. Okay, so let's see where we are going through. So anyway, the slopes on either side look the same. V out is equal to Vn for the very negative values. And for the very positive values, you get this R2 over R1 plus R2. But doesn't look like we go through zero because we've got an offset on our line here. We've got an offset. So let's look at the crossover point. Draw this longer. So here we got V out is equal to Vn is equal to, I'm going to just rewrite this guy. So these, again, these two, this has to equal to this at the crossover point. Okay, so I'm going to make those equal to each other. Sorry guys, my pen is acting up. Vn R2 over R1 plus R2 plus VD on R1 over R1 plus R2. Again, I'm just grabbing that stuff, putting it here. I'm putting this over here. These two have to equal to each other at the crossover point. Okay, so now I start moving stuff around. So I bring this guy over to the other side, separate out Vn. So let's see, these two guys cancel each other out. So Vn is equal to Vd on at the crossover point. And we also know at the crossover point, V out is equal to Vn, so that's also equal to Vd on. So if I was going to draw this, so draw this. Okay, so V in, V out. Okay, looks like the crossover point is when V in is VD on, and when V out is VD on, whatever VD on is. So the crossover point is here somewhere. Okay. And below this value, V out is equal to V in. So this is going to be a straight line again, one. And beyond this value out here, we're going to have this ratio. So let me do this. Oops. Okay, so this was for what we just did, which is the constant voltage model. And this was the one we did before that for the ideal model. And notice that they look the same, except we basically moved this crossover point to an offset of VD on, V in, VD on, and V out is VD on. Okay, so that's what happened going from the ideal model to the constant voltage model. Okay, now you could have guessed this, I guess, if you just look at the circuit and looks like a voltage divider going to a battery instead of ground. But sometimes, at least, you know, I don't know, for me, sometimes it ends up being some funky place with some resistive divider type of thing. And we'll see that kind of in the next example, but hopefully it'll be a good lesson there. Any questions about that? What we just did?
Professor, I have a question.
Yeah, Kevin.
Could you scroll up to where you had VD is equal or set to very large? So right there where you have it drawn, it's supposed to be a closed switch right above the circuit schematic, right?
Oh, yeah, yeah.
Where you
All right,
have.
thank you. Thanks
Okay.
for bringing that up. Yep. Thank you. Thanks, Kevin. Is everybody good, or should I keep going, or do you guys need to? People still copying? I'll keep going then. All right, guys. So let's do this. Let's do another example. It's tiring, but we gotta just be. The homework is like circuit after circuit like this, just to make sure you guys cannot go wrong. Okay, so this one, why don't you guys give it a shot? And then I'll ask one of you guys to help me solve this problem. So why don't you guys take about 5 minutes trying to work this? Okay, guys. Let's see if we can work this out. So first, so this is again constant voltage model. Let's look at the case when Vn is minus infinity. So Arthur thinks he got it. So Arthur, can you give me a hand here? What'd you get?
I think it's just for drawing itself.
Okay. Do you want to help me draw the schematic?
I can do that.
Okay.
At least I'm hoping I can do that.
Sure you can. Let's start with Vn. Okay. Well, first of all, let me see. What happens to the diode? Is D1 on or off?
Well, it's going to be off, right?
Because this guy is very negative, and this point is very negative, and it's going to be off. That's right. So D1 is going to look like that.
Open circuit.
Yep.
So you can effectively just draw the schematic the same way, except you remove D1 altogether.
Yep, exactly. So R1, R2. I always just draw the D1 anyway, just for the sake of completion. But yeah, I could just get rid of it. Okay, and then what would the equation look like with V out versus V in? So it's gonna just look like a resistive divider, right? If this thing is gone, you just have these two resistors.
Yeah, two resistors.
Yeah. So it's just a resistive divider. Do you remember the resistive divider equations? Or equation? It's just basically R2.
It's R2 over R1 plus R2.
Yep. Okay. Yep. All right. Thanks, Arthur. Any volunteers for VN plus infinity?
Did I go?
Okay, Kevin, go for it.
So the diode, it's going to be represented by a closed switch and a battery.
Okay, so VN 1 or 2, and I have a closed switch and a battery here, and V out. So
So
what's
then V out would just be the voltage of the diode, VD.
Yep, let's just be VD on. Yep, got it, Kevin. Kevin, you want to help me with the crossover point too?
So then you said V out equal to R2 over R1 plus R2 times Vn equals.
Okay. So we've got, so this, so what does V out look like at the crossover point?
Is it going to be offset from the
Well, let's work out Vn first. So like this is an equation you can use, right? Half of it. So if I just look at that equation for Vn, okay, versus Vd on. Like remember, Vd on is a constant. So all you do is you just basically say Vn, you move this stuff over. So it looks like R1 plus R2 over R2 VD on. So basically it's R1 over R2 plus 1 VD on. And this already tells us V out is equal to VD on. At the crossover point. You good with all that, Kevin?
Yeah, I just didn't know how to solve the problem.
Professor, could you zoom out so I can see the whole page real quick?
Sure.
Gotcha, thank you.
Sure. So Kevin, what confused you there with the crossover thing? You
I
got-
wasn't exactly.
Go ahead.
I wasn't sure what. Excuse me. I wasn't sure what we were solving for. So in this case, now that I see the graph, where we have V out, a function of V out and V in,
Uh-huh.
I see now that we were solving for V. If I'm understanding.
Yeah, you're solving for V out and V in sort of in terms of everything else. Okay, so are they equal to 0? Are they equal to some offset, whatever? So here, when you say this has to be true and this has to be true, right? This already tells you, okay, V out is VD on at the crossover point. So you don't have to like guess at that one, right? This one was already, this relationship is already, because I'm saying V out, this comes from this side. This comes from this side, right? So V out is just equal to VD1 because all sort of everything's equal here. Okay.
Okay, so here we have V in then.
Yeah.
We now solve for. Okay, I see.
Yeah. So if you, when we plot it, I'm going to plot Vn versus V out. Okay, Vn is going to be somewhere here, and its value is going to be 1 plus R1 over R2 VD on. Okay, it's going to be this guy. Okay, and then V out is going to be VD on. So it'll be up here. So the crossover point will be here. And anything past this point is going to be V out is equal to VD on. And anything below this point is going to be still going to go through 0, because notice that here at V in is 0, V out is going to be 0. So it's still going to go through 0, 0. And the slope is going to be R2 over R1 plus R2, which is this guy. Does that make sense?
If I could ask, how did you get that past the crossover point? How is it as
This point here?
yeah
So
to the when
so all I did was I said, I'm kind of doing the same things I'm always doing, except this one got a little confusing. So let me erase it and start. So this is for a very negative value. This is for a very positive value. At the crossover point, they both have to be true, right? So you have to, you basically, because those two lines, there's going to be a line like this, which is this guy. And then you're going to have a line like this, which is like that guy. And at the crossover point, they both have to have the same value. Now, you don't know if it's going to look like this, or is it going to look like that? You know, you don't know where the crossover points are, right? Could be any one of these places. Okay, so to figure out where the crossover point is, you basically set these two equations equal to each other. So I'm just going to rewrite it. So V out, so this is just this guy, is R2 over R1 plus R2. V in is equal to V out is, I mean, it's equal to V out, right? V out is equal to, so that's this guy, right? And here, this guy, V out is equal to VD on. Okay. Are you with me now, or Kevin?
Yeah.
So far? Okay. So do you see how this equation basically tells you, so you want to find out two things at the crossover point. The crossover point has a value for Vn and a value for V out. Okay. I mean, it could be 0 and 0, could be, you know, VD on and VD on or something, or it could be any combination thereof, but you would want to find out a Vn and a V out value. And it could be, you know, the crossover point could be here, it could be here, it could be here, it could be here, it could be anywhere. So you got to figure out where it is. Okay, so first, V out is pretty easy because V out is equal to this, but it's also equal to this. So you just know V out is equal to VD on. So we don't have to do any work for the value of V out at the crossover point. It's just equal to VD on. So that's how, so I basically plotted here on the y-axis. Okay. Now the question is, where are we on the x-axis for the crossover point? And for that, I'm solving this equation, which has got Vn and Vd on, which is R2 over R1 plus R2. Vn is equal to Vd on. Okay, and I'm just doing Vn as R1 plus R2 over R2 VD on, which ends up, I mean, I just rewrote it in a slightly different way. So that ends up being the Vn value. This ends up being the V out value. So that gives you this point.
Okay, that's completely clear now.
Okay. So one last thing to worry about is, and this is like, you know, I've done these homeworks before and like these problems over and over again. Sometimes you go, Jesus, is it gonna go like through, you just gotta make sure it goes, because you don't know, the problem doesn't give you the values for R1 and R2. Okay, so you gotta kind of make sure we don't end up, you know, above or below the origin. So also knowing that the crossover point is above here, basically I know this, or sorry, that over here, then Vn is 0. I want to make sure V out is not some funky value out here and here. But because the crossover point is here, this whole part of the equation, this whole area has to be V out is R2 over R1 plus R2 Vn, which is this guy. Oops. So when Vn is 0, in this case, V out is equal to 0. So it's crossing the origin. So it's like just another data point there for me. Okay. Any other questions from anybody?
Professor,
Yeah.
do we always pass through the origin?
No, you won't. So you got to be a little careful about testing where, you know, where the origin is or a few points. Don't make any assumptions, because imagine like, because you're not given R1 and R2, like sort of weird things can happen. It could have put you like here or here. But again, because anything below the, so this is the crossover point. Anything here has to follow this equation. So I can actually check for Vn equal to 0, what is V out? So Vn equal to 0, V out is going to be also 0 given this equation. So I know, I double check that to make sure it does go through the origin, but it doesn't always have to go through origin.
Okay, one more question. Would you explain one more time how did you get V out equal VD on?
Sure. So all I'm doing is, so let's see. Let me just keep erasing this thing, and I think that is the most confusing part of this. I think for me anyway, this part about looking at things in a very negative value, looking at things in a very positive value, that always kind of made sense. And then there wasn't like a lot of guesswork. So, but the crossover point is always difficult to get in your head. Now, I'm not going to do a problem here, which, you know, you're going to have problems like that in the homework, but like you could have a situation like this, okay, where you have multiple diodes, okay, and you'll have multiple crossover points, okay, so it can get confusing. So, you know, you guys have like every right to be confused at this point or figuring out what to do. But basically the way I look at it is you have a situation where you're very negative and the diode is off. And then you get very positive and the diode turns on. At some point, the diode goes from being off to on. It has to happen at a very
Oh,
specific.
so sorry to interrupt you, but
Uh-huh.
my question was only on the positive side. How we?
Oh, here?
Yeah,
Oh, I'm
that's.
sorry, Blake. Thanks for stopping me then. So basically,
Well, the thing is, you erased. Can you redo that?
sure. Well, this is just a,
You.
oops, what the heck am I doing? Sorry, let me, here we go.
Yeah, that's perfect. So what I like kind of threw me off, just when on the right side when you said V out equal VD on.
So,
Yes,
okay, good. So you saw how we got this equation, right? For very positive.
that's the part that I'm not getting.
Okay, gotcha. Okay, so look at this. So did you see how we got this schematic? So we just said the diode is on. So basically, so you have a battery connecting to V out.
So
Okay.
so I'm assuming since V out, you said equal VD on.
Uh-huh.
So we're not getting any voltage from V inside.
So you would, but this thing is the resistance of this is 0. Okay, so this is another way to look at it. So let's say you do get a voltage from the V inside. Okay, what's that voltage gonna be? Well, the voltage from the V inside is gonna be V out. If I just do a KVL from the inside, right? It's gonna be Vn minus the voltage drop across this resistor is equal to V out. Okay, you with me, Louis?
Yes.
Okay, so now the question is, what's the voltage drop across this R1? Well, the voltage drop across the R1 is like this guy. It's kind of a circular argument. This battery puts VD on here. So the voltage drop across this R1 is Vn minus VD on. And the current going across here is Vn minus VD on over R1. You with me so far?
Yes.
Okay, so basically if I want to do a KVL here, I'll do Vn minus I R1 minus V out is equal to 0. Let me move this stuff out of the way. So Vn minus, so I'm going to just use this I. So basically I end up with V out is equal to VD on.
Okay, now it makes sense. Thank you so much.
Well, it kind of is like a very circular argument. I think you have a few different ways of looking at this, okay? You have, one way to look at it is whenever you have a battery or a voltage source connected to a node, and you have anything like a resistor or anything else hooked up to that node, this guy always wins. If it's connected directly to a node, this guy always wins. Why is that? It's because it'll be able, just by definition of a perfect battery or voltage source, it'll be able to sink in whatever current comes across R1. It'll sink in whatever current across R1 is required to make this point VD on. It has like infinite capacity for pulling current, okay? So that's like a definition of a voltage source when you're looking at it from a circuit analysis point of view, is it will enforce a voltage here regardless of how much current it has to sink or source. That's like sort of by definition. And your voltage sources in the lab work to like that to some extent. I mean, they'll have an upper limit. It's a large upper limit on current, but they'll sort of force that. So one way to look at it is this guy will just force whatever current through R1 that it needs to make this point VD on, and then it'll pull all that current down to it. They'll just sink all that current, if that makes sense. So, and I just think whenever I see a voltage source hooked up straight to a point, I just say, man, that's it right there.
I'll keep that in mind when I do the homework.
Okay. Sometimes what happens is, I think this happened last lecture, you end up with this kind of a situation where you have like two voltage sources trying to drive a node. And that, like, you have to make some assumption. One of them is going to win, and you're going to have to make an assumption about which one. And that's, I'm going to admit, that's like, it could go either way in that case, but it's pretty rare when that happens. Okay, guys, so let's see. Let's do one more. And this one I'll just do like a flat out because we're kind of running out of time here. But it's yet another, it's the same thing. Like, again, it's like doing the same thing over and over again, but each time we're, the equations look a little different. Okay. So this one, again, a constant voltage model, and basically this one is, so these, hopefully you guys are at least seeing how, if nothing else, you guys at least see the benefits of these simpler models, because if for any of these things we still were dealing with the exponential model, man, our equations would be pretty hairy. In this case, I mean, it is slightly complicated, but it's pretty straightforward. We're just making very simple assumptions, very simple math, no exponentials, no logarithms, no iterative procedures. So if nothing else, hopefully you guys are seeing like how this kind of the constant voltage model, or we're doing mostly that today, constant voltage model makes your analysis simpler. Okay, so again, Vn is negative. And for that, now this time, when Vn is very negative, notice the diodes cathode is connected here. So when Vn is very negative, the diode actually turns on. Okay, so I'm going to, so diode D1 is on. Okay, so it looks basically like, sorry, let me write it. Another tricky thing to watch out for is make sure you've got the direction for this battery right, the minus and the plus for this battery right. Okay, because you could easily flip it, if you're not being careful, flip it on the other side and it's going to screw up your results. Okay, R1, V out, V in. Okay, again, in this case, basically if I do a KVL, it's Vn minus Vd on is equal to V out. So, or again, KVL says V in minus Vd on minus V out is equal to 0. No, I'm sorry, it's not minus. Yeah, I screwed this up already. It's plus because this battery is minus to plus. So it's going to be V in plus Vd on minus V out is equal to 0. So V out is equal to Vn plus Vd on. Okay. And then when Vn is plus infinity, D1 is off, meaning that circuit's going to look like this. Okay, in which case this guy is completely out of the loop, so to speak. So we just have a voltage divider. So we have V out is R1 over R1 plus R2 V out. Okay, so now the crossing point, crossover point is these two equal to each other. So V out is equal to V in plus Vd on is equal to R1 over R1 plus R2 V out. Okay. Oh, sorry. I have too many V outs here. So this should,
Professor.
yeah.
Oh yeah. I was about to ask you on that.
Okay, thank you. Like, why do we have so many V outs? Okay, so then the first thing is we can calculate Vn. Okay, so we basically use that part of the equation. So Vn plus Vd on is R1 over R1 plus R2 Vn. So gathering Vn's 1 minus R1 over R1 plus R2 is minus Vd on so Vn is minus R1 plus R2 over R2 Vd on. Okay, and then V out is Vn plus Vd on, right? Vn plus Vd on. So it'll be minus R1 over R2 plus 1 Vd on plus Vd on. So these two, basically this guy and this one, so you end up with minus R1 over R2 Vd on for V out. Okay, so if I draw this, so I think this goes back to Louis' question about does the curve have to cross the origin? And this is a case where it won't, right? So in the crossover point, Vn is a negative value. Okay, so it's minus 1 plus R1 over R2 Vd on. And V out is also a negative value. So V out is minus R1 over R2 Vd on. So the crossover point now is negative Vn minus V out. And anything below this point is V out is Vn, okay, plus this offset, but basically it looks like a line. And anything above this point is this resistive divider equation. So it's, I guess it does go through the equation. Sorry, I guess it does go through the origin still. So V at R2, was it R2 over R1 plus R2? No, it's R1 over R1. And the reason I know it goes through the origin is anything above here, it has to this equation. So when Vn is 0, V out has to is equal to 0. Okay, guys, I'm going to stop here, but I think you get the idea of, we could keep going this, and the homework does sort of keeps doing these kind of solutions just to get you guys used to analyzing these kind of circuits. And so basically you got these three models, the constant voltage model and the ideal model, help you do the analysis this way. When you do the exponential model, you basically have to do the iterative procedure that we used, a few lectures back. Any questions?
Not for me.
All right, guys. Good luck. I mean, I would really, as you can tell, I think it's good idea to do the homework for this one for sure. Otherwise, the quiz is going to be going uphill.
When is the quiz?
What's that? When is? I think I'm going to put it not this coming Tuesday, but the Tuesday after. So because we got to, I think we'll probably finish chapter 3 either Tuesday or early Thursday, and then you guys will get the coming weekend to also study for the quiz. So what is
Thank
that?
you.
Probably March 9th or something, but I'll put it up.
Professor?
Yeah.
So the quiz is going to be on this specifically?
Yeah, the quizzes are all, they only cover the stuff from the last quiz. So the quiz is going to cover, quiz 2 is just going to cover chapter 3, whatever we cover in chapter 3.
Oh, okay. So this isn't the only thing that'll be on the quiz.
No, we're going to sort of do the stuff like we have some stuff still to cover on chapter 3.
Gotcha. Okay.
Yeah.
Yeah.
Okay. Thanks, guys. Take care.
Thank you.
Thank you,
Thank you,
Professor.
Professor.